Welcome to Dr. BT's Chemistry Essentials, A-Level Chemistry Made Easy. This video is intended to follow on from the previous video on the rate determining step. What we're doing in this video is we're looking at how the rate equation can tell us something about the mechanism of a reaction. Specifically looking at a very common exam style question, which is the difference between nucleophilic substitution, SN1 and SN2. So this is a common exam question on the rate determining step. I want you to pause the video here and just have a read through the exam question. So hopefully you can see here that we have a nucleophilic substitution. We're taking the haloalkane, whether it be T-butyl bromide or 1-bromobutane, they're both haloalkanes, and we are doing a substitution of hydroxide ions to form an alcohol. The difference is T-butyl bromide, when you draw out the structure, is a tertiary haloalkane. On the other hand, the 1-bromobutane is what we call a primary haloalkane. And so the substitution with the hydroxide ion produces a tertiary alcohol in the case of T-butyl bromide, or a primary alcohol in the case of the 1-bromobutane. In chemistry, we call these nucleophilic substitutions SN reactions, with the S standing for substitution and the N for nucleophilic. They are then designated by a number, 1 or 2. And this number tells you the number of species involved in the rate determining step, so the slowest step, otherwise known as the reactants in the slowest step. So if you have just one reactant in your slow step, then it's going to be SN1. If you have two reactants in your slowest step, then it will be SN2. Now if we then focus in on this part of the question, we're told that the equation in 3.2, which is the equation involving T-butyl bromide, has the rate determining step, or the slowest step, as this. It's the tertiary haloalkane converting into this tertiary carbocation and bromide. And just so you can see how this links, what we've got here is our tertiary carbocation is this here. Obviously the bromide is separated, and in order for that to happen, this carbon-bromide bond has broken. So the covalent electrons in that covalent bond have moved on to the bromide, and we've got this. And as it's the rate determining step, we therefore know that this is the slow step. We therefore must have a second step involved in order to capture this carbocation and form our alcohol, and that would be the hydroxide attacking it. So what we've done there is use information about the rate determining step in order to construct a viable mechanism to explain it. We've looked at the overall equation and used that plus this to create a mechanism. Now this one would be called an SN1 mechanism because we only have one species in the slow step. As there's only one of these haloalkanes in the slow step, we know that the rate equation will look like this, and it's first order with respect to this haloalkane, and it's zero order with respect to the hydroxide. So when it's asking you what can you work out about the mechanisms, we've come up with a mechanism. We've got the orders of reaction. We know it's first order for the T-butyl bromide, but zero order for hydroxide, and we've developed a rate equation for it based on the information given. Now, the reaction in equation 3.3 is the primary haloalkane converting to the primary alcohol. We're told it occurs in a single step. So we have to come up with a mechanism that combines both the haloalkane and the hydroxide all in one step to produce our product and the bromide separately. Now this is typical of the year 1 mechanisms that you learn for haloalkanes. It'll be this mechanism that is less familiar for most students. So what is going to happen is the following. The hydroxide and the haloalkane are going to be the first step, and as there's the first step, there's nothing to compare it against, so we could technically call this the slow step. This is then going to attack the delta positive carbon on this carbon halogen bond. Then what's going to happen in exactly the same step, this is going to have to break, because if we were to form a bond between the oxygen and the carbon here, carbon would have too many bonds, it'd have 5 bonds, so it immediately has to break this bond, forming the bromide separately and our primary alcohol. Now, because there's only one step, so this must be the slowest step, and there's 2 reactants in it, this is known as an SN2 reaction. As there's 1 molecule of the 1-bromobutane and 1 molecule of the hydroxide, your rate equation is going to be first order for each of these. And so what you've done is taken some information in the question and proposed a rate equation and a sensible mechanism that fits that data, and you've got 6 out of 6 marks. Now, whilst this is an apply question in OCR, so it's using rate equations, etc., in other exam boards such as AQA, you are expected to know what types of haloalkanes do the different types of nucleophilic substitution. So tertiary haloalkanes always undergo SN1, so this type of mechanism where the slowest step is just involving the haloalkane. Primary haloalkanes always undergo SN2, so both the hydroxide and the dissociation of the carbon-bromine bond happening simultaneously at the same time in one step. Whereas secondary haloalkanes can sometimes undergo SN1 and sometimes can undergo SN2, so you ought to be ready to be able to devise a mechanism, both types, SN1 and SN2. Now, the reasons for this, again, aren't needed for OCR. However, it is all to do with something called steric hindrance, so the amount of space. With a tertiary haloalkane, if you were to try to get this hydroxide to come in and attack this carbon and therefore break the bond, like in an SN2 reaction, these carbons attached to the carbon where you're going to be attacking provide too much space. They take up too much space, and so this can't actually attack. Whereas obviously in an SN2 or primary haloalkane, the carbon you're trying to attack has 1 carbon attached to it, but then the other 2 are really small hydrogen groups, whereas these are 3 big carbon groups with hydrogens around it, methyl groups. And so the OH can attack a primary alkane like so. So this concludes this video looking at a specific type of exam style question on SN1 and SN2 reactions when dealing with rate equations and rate determining steps. If you found this video useful, please like it and then ensure that you subscribe to the channel so that you can get all the videos as and when they're uploaded.